the change of basis. And today we are going to cover an example just to refresh our knowledge. And then we are going to see the beginning or the first cases of how we are going to use the diagonalization. So we want to change the basis. Okay, so we do the linear transformations, and let's use our general schema, which I use it a lot. So let me try to draw here. So let's assume here that we have a basis B1, okay? And then here we have a standard basis SB, and then we have also another basis B2. Now, so far, we have studied the linear transformations. And the linear transformations, they operate, they are like an operator which operate on a specific vector X or on a data set. And this is equivalent to a matrix A multiplying the vector, right? So this is how we have seen it so far. Now, the relationship with the change of basis, so we started with the discussion with the basis change. Now, what was the basis change? The basis change, it is just the representation of a single fixed point. So imagine, you have a single point here, and we want to find how does this one project on the standard basis. This could be, let's assume this is something like 2, 1. Assume this is 2, 1. In standard basis, this is 2, 1. Then how does this point project onto a different basis, which would be something like this? Here and here. So how does this point, so the projection on the standard basis is this, the projection on this other basis, this is going to be something different, and here, so this could be something like 1.5 and 0.3. 1.5 and 0.3. But what is essential is that this is fixed depending on how it projects. This means that this is how we can do the basis change. And in order to do this, so let's look, for example, what is the standard basis? What is it? What are the vectors which define the standard basis? Can you help me here?
E1 and E2.
E1 and E2, or 1, 0, 0, 1. What is basis B2, B1, which we denoted here with red? Approximately, this is not to scale, but this is like 1, 1. So one of the vectors is 1, 1. The other vector, it is 1 minus 2, okay? 1 minus 2. So this would be a different basis. And what we traditionally do, we see that there is a matrix P, which in fact, this matrix P is equal to what? We use these vectors, 1, 1, 1 minus 2, okay? So we use these vectors to transform any vector in this domain into the vectors in the standard basis. So in this case, we generally write that X, or we can say it like this, any X, if we do not denote any other notation, we understand that we are talking about the standard basis, okay? So writing nothing is equivalent to writing this SB, standard basis. This would be equal to P, the matrix P, which is composed of the same vectors, times the vector X according to basis B1, okay? So this is what we mean with regard to the basis change. Now, the linear transformation and the basis change, so let's denote here, this is rewriting the vector, okay? So let's denote it like this. This is rewriting the vector, and for this one, this is all that we need. So we go this way with P, we come back with P inverse. Now, the situation, it is a little tricky when we transform a specific linear transformation. Okay, so now we assume that here we're going to have a matrix A, and this matrix A, it represents what? It represents a specific linear transformation. How does this linear transformation look into a different basis? This is going to be represented by some matrix. Let me write, how can I write this one? Let's say matrix D, D1. And this matrix D1, the transformation, it is not as simple as this, but we denote this as follows. We say that this new matrix, this is equal to P inverse times A times P. Okay? And let me just look if I can find a specific example. Okay, no. But so I want to note that it is good. We want to change how a vector looks from one domain to another. We looked at these examples. We solved examples last week. We're going to solve one example today to kind of remind you again of this aspect. Then we come back to the linear transformation, which is represented by a matrix. It is not as simple by just multiplying by a matrix like this, but we have to multiply with P inverse times A times P. And this is how the linear transformation is done. Okay? We are going to write also a complete theorem, but for the moment, we are just providing a general, the general perspective of the course. And at this time, you might even take notes of the major aspects so that you don't forget them. The theorem, which we're going to provide in detail, can be summarized as this. Any matrix A represents linear transformation LT in standard basis. Okay, so this is then P inverse times A times P represents the linear transformation in the basis D1. Okay, so this is how the linear transformations are projected onto different bases, and this is how the vectors are projected into different bases. So we need to keep this, to remember this. Now I believe with examples, it might be easy for us now to remember this. And with the linear transformations, we're going to study this in detail, and we'll try to make it clear to all of us that we're going to remember. We should not forget this, sorry, we should not forget this, because this is the most important part of the linear algebra. So with regard to me, forget about the solution of linear system of equations. Forget all of those. Those are only to teach you or to train you on how you perceive the range of a specific matrix, okay? They are very useful, no objection to that, but the essential, the most important aspect is the basis change of the linear transformations. Now, regarding the theory of the matrices and properties of matrices, we can say that for any vector D, sorry, for any matrix D and the matrix A, if we have a matrix P, and then if we can write such a relationship like this, then we call the matrix D and the matrix A, we call these as similar matrices, okay? And similar matrices, they have some properties together, okay? But we should remember also this one. Now, in essence, this is where last week, I remember one of you asked me, which basis should we use? This is the best question to ask, because we're going to see that in order, this will be a tricky question. So for any data representation or for any combination which is provided or given by matrix A, we want to simplify the problem. But to do that, we have to search for all the possible bases. In principle, it might be we have an infinite number of bases to choose from, and we're not going to test all of them. And for this reason, we should have, it would be very good if we had the possibility to pick up the best basis with a well-defined procedure. Luckily for us, we have this well-defined procedure, and the best basis out of which is one of the, with an infinite number of possible solutions, the best basis B. So let me write this like this. So the best basis would be one that can be found by the eigenvectors. And this one, we are going to learn this by the end of today's session. Okay. So, reminder, final word in one sentence. Vectors are projected from one basis to another like this, the simple way. The linear transformations, it's a little more tricky, but it's not the end of the world. It's just that you define a new matrix, which is equal to P inverse A times P. Now, let's see an example about the vector transformation, or the vectors being projected onto different bases. And let's assume we are given that we have a basis B with which is defined by these vectors 1, 2, minus 1, 1, and we have another basis S which is defined by 3, 1 and 5, 2. Now we have given that X in basis B is equal to 4 minus 1. Find what is the vector X according to basis S. Okay, so this is what we are given, and we have to find what is in vector in basis S. Now, regarding this, let's try to use this space here. So initially, and we can also change these in fact. So what is the first basis? It is 1, 2 minus 1, 1. 1, 2 minus 1, 1. Here we have the standard basis, that's the same. And the other basis S, this is defined as 3, 1, 5, 2. Okay? 3, 1, 5, 2. Okay. So let's move on. We have.
May I do this one?
Sorry?
May I do this one?
I cannot. I don't hear. What do you say?
May I give an idea about this exercise?
Sure. Yeah, you can help me. What should we write down here?
At first, we should write that X projected in S equals to PS prime, PS inverse.
Okay, so this is X according to the standard basis, right? Or what did you say?
No, X projected in S.
Yes.
What is required? Equals to PS inverse.
Yes.
Multiplying the P in basis P, and multiplying X projected in basis P.
That is correct. So this is all that we need to do. So apparently,
we can substitute because we have all of them given in the exercise. So we can write the first one, which is going to be 2 minus.
What is PS? What is PS? Do you see the PS on the board?
The PS is 3, 5, 1, 2. So we need to find the PS prime.
Wait a second. So you said PS is equal to
3, 1, 2.
What about PB?
1, 2 minus 1, 1.
Yes. What about PS inverse?
To find the PS inverse, the first step is to check the determinant. 3 multiplied by 2 minus 5 equals 1. Since the determinant is 1, this is a matrix, I would say. To find the matrix, we go to 3 with 2 and we check the values of 2 and 1 to make them 9.
There is some echo. Are you keeping your microphone close to your? Can you keep your microphone?
No, with my PC.
Because the sound it fluctuates a lot. Anyway, but it looks like you are correct. We do it like this. So this is the transition matrix which can help us transform a specific vector from this basis to another basis. And let's do this one step by step. And let me ask you one other thing. This matrix S, the determinant is equal to 1. What do we call these
unimodular matrix.
Okay, this is unimodular matrix. This is unimodular matrix, but then I'm going to assign you, you have an assignments data, and also the others in the class. You can also solve this one during the break. Can you find what happens if we use this PS? Not what happens. Can you find how this unimodular matrix behaves if we multiply this PS, okay, to the power n times any vector which is 1, 0. Okay, so Stella, this is your assignment, and the others are also welcome to work this one. So here, sorry?
During the break or not?
Well, you can work it now. I think it shouldn't take you, you can start it from now without losing too much attention, or during the break, okay? But what we're asking here, you multiply P on this 1, 0. This is going to be AB. And then you find what is P on AB, all right? So we get here CD. And then you multiply with P this, but you mean, once we apply the P twice, this is going to be P squared times the original vector, which was 1, 0. Okay? So apparently this is a unimodular matrix. So then have a look at what happens here. So now, let's start with this part. This XB, what is XB?
4 minus 1.
That's 4 minus 1. What was PP? I think we wrote it.
1 minus 1 to 1.
Yes.
And P inverse was 2 minus 5 minus 1, 3.
Yes. Minus 1, 3. And let's multiply them.
We can at first multiply the 4 minus 1 with PB.
Yes.
To get the standard basis.
That is true. So what we get here is
5 and 7.
So this means that this vector, it is 5 and 7 in the standard basis. In the other basis, this was 4 minus 1. 4 minus 1. So, and in fact, we can also look at the problem like this. If the vector here is 4 minus 1, that means that the 4, it projects onto this vector 4 times, and this one is minus 1 multiplying with this vector, right? So it is equivalent to reporting the following. We can have 4 times 1,
2, minus 1.
4 plus 1, 5, 7. So it is the same result. This is what we should be getting. This is the standard basis. You were correct. And here we get
2 minus 5 and minus 1, 3. We multiply this to get minus 25.
Minus 25 and then?
And 16.
16. So
now also I think that we could write this in the same way you wrote the 5, 7. For example, we can write minus 25 that multiplies 3, 1 plus 16 that multiplies 5, 2. If I'm correct, I'm not sure.
That's true. So this one, it will be, you are right, this is going to be minus 25 times 3, 1 plus 16 times 5, 2. And this should be equal to minus 25, this is minus 75 plus 80. We get a 5 minus 25 plus 32, we get another 7. So we see that these are the same, because what we are doing here, we are multiplying the original vector minus 25, 16, which is according to basis S, which we can denote it here, and we are multiplying here with this matrix, which is 3152. 3152. And multiplying 3152 with this means that we are kind of multiplying the minus 25 with the first column and the 16 with the second column. Why is this? It is because we always multiply the first row with these two numbers, right? And the 3 multiplies the minus 25, and the 5 multiplies the 16. Again, if we multiply the second row, the 1 multiplies the 25, and 2 multiplies the 16. So it is obvious that whenever they are combined, the 25, which is now in red, it multiplies the first column, and the 16, which is now in black, it's going to multiply this element, which we see also down there. Okay, so this is how, this was an example, just as a final reminder of how we conduct the basis change. And now we want to talk about the change of basis. So I believe this is clear, right? This part here. I thank you for your help. And we should not use, we're going to write this on the side so we don't lose this. PS, this is equal to 3, 5, 1, 2. Determinant is equal to 1. And let's move to the next topic, which will be the discussion of the linear transformation change of basis. So allow me to erase this one.
Professor, I'm sorry for interrupting. Can you write the assignment that you gave us one more time, please?
Yes, the assignment is this. I'm going to keep you for some time. So assuming that we have a PS, which is equal to 3512, find what is Pn times 10. Okay, this is what you should find. I can write here homework, and yeah, okay, which is actually, it's also written here, but maybe I erased the PS, so let me leave this part here. Now, let's talk about the change of basis and the similarity. First, I'm going to write the theorem in the formal way. Now, the general idea of this linear transformations change, when we change the basis, how it's done, is already in the board. So whatever message you need to take home is already here. But let's provide here also the formal theorem. The theorem, it states that for any linear transformation T, which is, wait a second. Okay. For any linear transformation T, which is going from Rn to Rn, and in fact, if we have a linear transformation from Rn to Rn, what is the matrix which represents this linear transformation? It's going to be a matrix A, but which is a square one, okay? Because it's going to be A n by n. So for any linear transformation that looks like this, and for any basis B, which is equal to x1, x2, and xn, so this is the basis, right? And let the linear transformation on a vector x be equal to A times x. And let P be equal to x1, x2, xn. Now, so the B is a basis, T is a linear transformation, P is a transition matrix. So the transition matrix, we are talking about matrices that help you go from one basis to another. So we're talking about these, okay? And how are these transition matrices composed of? They are composed by columns which come from the basis B. So this B is the basis. This P is the transition matrix. This T, this is the linear transformation LT. So you can read it like this. So this is what we are given. And by the way, if this is from Rn to Rn, we immediately notice that this A is going to be a square matrix. Okay? And then we can say that okay. Now the formal, so this is what the theorem is about, and the result, it will be in fact the following. The matrix A, which is a square matrix n by n, it represents a linear transformation in the standard basis. And this other matrix P inverse A times P, it represents this linear transformation in basis B1 or in any basis B. So this is what the theorem is stating. And this is also a reminder with a general definition, which we can provide it like this. So definition, if A is given, and if P exists and is invertible, okay, so we are given the general definition of the similarity of matrices. If A is a given matrix and if P exists and is invertible, then D, which is a matrix, defined as D is equal to P inverse AP, is called D is similar to A, okay? So matrix D is similar to A. And it looks like that linear, when we transform the linear, how can I say? So let's have a look at this one. We have the matrix A representing a linear transformation in the standard basis. Then we have a matrix D1, which is in this basis, and which is also a matrix D2, which represents this linear transformation in a different base. So similarly, we can have also D3, D4, D5. We have an infinite number of Ds, which are going to represent this specific linear transformation in different bases. But then we have the following. So if we have that D1 is similar to A, which is linear transformation in one basis, and if D2 is also similar to A, why? Because they are similar, because there exists a matrix P which allows such a definition of D2. This implies that D1 it is similar to D2. Okay, so these are just nice properties of these matrices as we are representing the same linear transformation from one basis to another. Okay, so this is the main idea or the main statements that we can provide regarding the linear transformations of bases during the basis change. Do we have any question for what we did so far? No, okay. The change of basis, okay. If you have no question, I'd like to stop this session because we are going to switch to another topic.